Hi, in this presentation, we will discuss the concept of bilinear transformation, which is an important technique used in digital signal processing, particularly in the design of IAR filters. This topic comes under Unit 2 of Design Digital Signal Processing. The goal is to understand how analog filter can be converted into digital filters effectively. Bilinear transformation is essential because real-time systems require digital filters for processing signals efficiently, while analog filters are already well understood and widely used. Digital systems demand stable and accurate implementations. The bilinear transformation helps convert analog filter design into digital filters without introducing aliasing, making it a reliable method for practical applications. Impulse Infinite impulse response systems are those in which the impulse response extends infinitely over time. This means the output depends not only on current input but also on past outputs. IAR filters are designed by considering this infinite nature of the impulse response, making them efficient, capable of achieving desired frequency responses with fewer coefficients compared to FIR filters. Analog filters are classified based on their frequency response characteristics. These are four basic types: low pass filter, high pass filter, band pass filter, and band stop filters. Each type allows or suppresses certain frequency ranges, making them useful in various signal processing applications. Bilinear transformation is a mathematical mapping technique that converts the S-plane of analog systems into the Z-plane of digital systems. Specifically, it maps the imaginary axis of S-plane onto the unit circle in the Z-plane. This mapping is one-to-one and depends on the sampling time period, ensuring a stable and accurate transformation. This slide illustrates how the bilinear transformation maps points from the S-plane to the Z-plane. The left half of the S-plane, which represents stable analog systems, is mapped inside the unit circle in the Z-plane, preserving stability. This property makes bilinear transformation highly useful in digital filter design. The process of bilinear transformation involves several steps. First, we specify the digital filter requirements. Then we perform pre-warping of critical frequencies to compensate for frequency distortion. Next, we design the analog IIR filter. After that, we apply the bilinear transformation, and finally, we obtain the digital transfer function of the filter. This slide compares the ideal and practical magnitude response of a low-pass filter. An ideal low-pass filter has a sharp cutoff, allowing only low frequencies to pass. However, practical filters cannot achieve this perfect transition and instead show a gradual roll-off. This difference highlights real-world limitations in filter design. For high-pass filter, the ideal response completely blocks low frequencies and allows high frequencies. In practice, however, the transition is not abrupt and some distortion occurs near the cutoff frequency. Understanding this helps in designing filters that approximate ideal behavior as closely as possible. A bandpass filter ideally allows only a specific range of frequencies to pass while rejecting others. This practical implementation shows a smoother transition around the passband edges. This concept is widely used in communication systems where only certain frequency bands are needed. Bandstop filters, also known as notch filters, ideally block a certain frequency range while allowing others. In practice, the rejection is not perfect and there is a gradual transition. These filters are useful in eliminating unwanted frequencies such as noise or interferences. Bilinear transformation offers several advantages. It eliminates aliasing and preserves the stability of the system during transformation. However, it introduces frequency warping, which must be corrected using pre-warping techniques. Its applications include digital audio processing and communication systems, where accurate filter design is crucial. This slide reinforces the overall concept of bilinear transformation by summarizing its key aspects, including its working principle, advantages, limitations, and applications. It helps in connecting all the ideas discussed in the presentation. This slide includes definitions of IIR filter, the nature of bilinear transformation mapping, classification of filters, explanation of the transformation process. These questions helps in testing understanding of the topic. Thank you.